recording. All right, so what we'll do today is the first thing is to go over the solution for the homework assignment that was due. Actually, that is to be due in about a minute because Moodle goes by the atomic clock time and not like the school's clock, which is off by a whole minute. All right, so, but I guess I can go over the solution now because I don't think people can type that fast and turn it in on time. So let's go ahead and take a look at the homework assignment. And this is the resolution one. The CNF one was already due last Wednesday. But that's the first one that we need to do, and then this is the second one. So I'm going to open up two tabs. Yep.
How is it possible to resolve it? I got no resolution because there's no Q to cancel it out with, right? Because you're trying to negate your Q.
There are two ways to end the process of resolution. One is you arrive to a contradiction, which means the theorem that you're trying to prove is in fact a theorem. Or you get to a dead end where you cannot add any new terms anymore. Because all the resolution have been quote unquote used up. So that's when you come to the conclusion and say the theorem is not a theorem because you cannot arrive at a contradiction. Okay, so let's go ahead and just do this part here. I'm going over the stuff from the previous homework assignment, and because that's the basis. So we'll go ahead and start with these. S is the easy one, is a CNF already, so we don't have to deal with that. P implies S is also pretty easy to deal with, because P implies S by the definition of implication, is the negation of P or S. And that is a CNF, okay? Because the negation of P is the negation of a single variable, and then S is a single variable, and the disjunction of these two is a CNF. So this is already a CNF. And then the last one is probably the more complicated one, and it looks like this. Q or R implies P. So the first thing we do is to turn it into, we get rid of the implication. So now we have the negation of Q plus R and the whole thing, or P. And this is by definition of implication. And then we apply De Morgan's law so that we we distribute the negation from the inside into from the outside into the disjunction, but then we have to change the disjunction into a conjunction. So now we have not Q, not R, and then plus P. And then now we can use the distributed law to kind of change this one. So it becomes not Q or P, and then not R or P. Okay, I think this is something that we talked about last time already. Are there any questions about this part? No questions? All right. So the single big CNF that we have at this point, without considering the theorem, is really just a concatenation or a conjunction of all of these items. So we have S all by itself as one item, not P or S as one item all by itself, not Q or P as one item, not R or P as the last item. So this is what we had last time, okay? A single CNF to capture everything that we already know is known to be true. Okay? Any questions about this part? Just a quick recap of the assignment due last Wednesday. Okay, so if there are no questions about this, then we'll move on to the homework that was due this morning. So in this case, the WFF, the well-formed formula of the theorem that we want to prove, is just a single Q. In other words, we're looking at these things and say, is it a conclusion? Can I conclude that Q has to be true because all of these things are true? That's the question. So the first thing you have to do is to take the negation of the theorem that you're trying to prove. So you have to say the negation of the theorem, of the proposed theorem, which means I'm not sure whether it is a theorem or not, is the negation of Q. Because the theorem itself is Q, so the negation is just the negation of Q. Yep.
So I remember last week you said each of the stuff in parentheses, but that would be one clause, right?
Yes.
What's the difference between a clause and a well-formed formula?
A clause is a well-formed formula, but it has to follow a particular format.
Okay.
So in this case, a clause can be a disjunction, but it can only be a disjunction of individual variables or the negation of individual variables.
Okay.
So that's a good question. So in this case, now we want to prove it. So to prove it, you basically just take everything that we have here, okay, and then you concatenate or just do a conjunction with the negation of the theorem, not with the theorem itself. And then we just need to perform resolution and say, okay, what can we do to resolve this? So we are looking for terms where one clause has a variable and then the other clause has the negation of the same variable. They're not really a whole lot. I think not P and the P can be resolved. So what I'll do is I'm going to highlight which two I'm resolving, just so that I can tell which one I'm resolving. So I'm resolving these two. Note how one has the negation of P, the other one has just P by itself. So when we resolve, we are not deleting any terms from the CNF. We are just adding the one as the result of the resolution. When you resolve two clauses, you remove the variable that is quote-unquote canceled out, because on one side you have the negated version, the other side has the non-negated version, and then for everything else you just concatenate. So in this case, we are just concatenating. In this case, S is on one side, and then Q, not Q, is on the other side. So we get rid of the P. Any mention of P or the negation of P is removed, and then we just concatenate the other parts to become a new clause. So because I already proved the step of resolution works, so we know that the meaning of this CNF is the same as the meaning of the previous CNF. Okay, it's just that we added one new term that is definitely not necessary. But the point is, can we get to a contradiction in this case? So let me see, can we resolve any further? So the more systematic way to look at this is to say, okay, let's look at the first one. What can it resolve with? Nothing, right? We look at the second one and we say, which one can it resolve to? Resolve with, okay? The next one, we did it already. We can resolve it with this one. There's one more. So we can go ahead and do this resolution. So I'm just going to highlight which clause is resolving with which other one. So these two obviously can resolve. So we'll go ahead and say, okay, but what do they resolve to? Is it something that we know already? Okay, so on one side we have S, on the other side we have not R. So that's new to us, right? So we just added a new term. Then we continue this process, and then we say, okay, what else can we resolve with this term here? We try the third one. These two cannot resolve with it, so we are done with those. So now we look at this term here and say, okay, what can resolve with this? We have not Q. Nope, nothing can resolve with this one. We look at this one here and go, okay, what can resolve with this one? Not R, okay, nobody has a non-negated R, so we cannot work with this one. And all of the other terms do not have a P, so it cannot be resolved. With this one, it cannot be resolved with any of the other terms because, we are looking for something that has a non-negated Q, and none of these two has a non-negated Q. And then the same argument applied to this one. We don't have a negated S anywhere else, after this term, and we don't have a non-negated Q after this term. And then we look at this one all by itself, it cannot resolve. So we are done, but we cannot get to a contradiction. We cannot get to zero, which means your conclusion is Q as a theorem cannot be proven. It is not a theorem. Okay, so basically we can say that no more resolution is possible. No contradiction. So as a result, Q is not a theorem. Yep.
Is it okay if we just put Q is not true?
You can say that Q is not true as a result of the other things being true. So it's a little bit more specific than just that.
There's no contradiction, so Q, what we're trying to prove, is not true.
It's not quite the same thing as saying Q is not true. We're simply saying Q is not guaranteed to be true because of the known to be true facts.
Okay.
which is not exactly the same thing as saying Q is not true. Q can still be true, it's just not guaranteed to be true because of the other things.
That's what I put based on what
Okay.
we found.
So I have to kind of look at your actual submission and see if the context implies that Q is not true as a consequence of all of the other WFFs. Yep, you had a question?
Similar, what if Q instead said the theorem does not follow? Like
That's fine. Yep, that's a good way to put it. The theorem does not follow is a good way to put it.
So I was gonna put theorem, but then I was
Okay, any other questions? Yep.
So if you get a contradiction,
Mm-hmm.
that means there's at least one case that it's true, or is it, or in that?
If you get a contradiction, it means whatever theorem that we're trying to prove is a logical consequence of all the known to be true facts. So it's guaranteed to be true if it is a theorem. If it's not a theorem, it simply means it is not guaranteed to be true, but it can still be true for some other reasons.
Okay.
Yep.
These are like, so I did the same steps when I turned it in, but can you just tell from the first step that it would be impossible to prove because there's no non-negated Q, and we can't introduce new variables into our system?
You can, well, there are two ways to prove things in this class, two easy ways, especially when it comes to Boolean algebra. One is to use resolution, because the resolution has to terminate. The other way is to use a truth table.
Okay.
So when you use a truth table on this one, then you will see the column corresponding to this and the column corresponding to Q, they do not match up. In other words, for each row, you cannot say, implication does not hold on each row. I'll put it one more time, okay? So when you look at each row, when you make a truth table, this value, the value of this column, does not imply the column of just Q all by itself.
Okay.
So you will find a column where this is true, but that one is false. And that, if you find a single row like that, that means Q does not follow the other one. Yep.
Now, I'm assuming this would be ugly and we really wouldn't want to do it, but couldn't we take that whole thing and put that it implies Q as a truth table?
Yes. If the implication holds for every single row, then it is a consequence of Q is a consequence of the other ones.
And we could put that in CNF that it would be ugly.
I'm not following why it would be. What is going to be ugly? The CNF itself?
Well, we'd have to put a knot on the whole. Is it?
No. But with the truth table, you don't need to negate it.
Well, I'm trying to think if there's probably a way to do it without a truth table.
Well, okay, there are three ways to do things and when it comes to proofs, especially with Boolean algebra. One is to use the axioms. The axioms are like commutative rules, like P or Q is the same thing as Q or P.
That's what I was thinking.
That's one. The second one is by resolution and also contradiction, which is what we're trying to do in this homework assignment. And then the third one is the use of a truth table, which is basically, okay, let's enumerate all possible combinations of true, false for all the variables. And then for each row, we want to see if the given facts or the given to be true well-formed formulae implies the other one. If it does, then the theorem is a theorem. It's a consequence of the known to be true well-formed formulae.
But if we're just going to use the rules, that's how we would do it then, right?
If you just use the rules, sometimes it's hard because when you use the rules, it's easy to do a direct proof, which means if it is a theorem, you can prove it. But if it's not a theorem, sometimes it's really difficult to prove something is not a theorem using a direct proof mechanism. And in this case, we have something that is not a theorem, so a direct proof is going to be hard because you don't know when to stop. You just cannot get to Q by itself, but you don't know when to stop because there are too many ways to proceed. Is that making any sense?
Well, I'm just asking when you start that setup, wouldn't you write it as S, and that whole thing implies Q, and then go from there.
We want to know whether it implies Q or not. That's a question mark. So what we are trying to do is to determine whether this expression here, this kind of somewhat gigantic expression, implies Q or not. That's what we are trying to find out. If it does imply Q, it means Q is a theorem of that whole CNF. If it does not imply Q, then Q is not a theorem. Is that making any sense? So if you use a Boolean algebra to try to prove this, the problem with Boolean algebra in this case is there are too many directions to go, because that you can apply any one of those rules and it doesn't get you to Q. So what do you do next? You apply some more, it doesn't get you to Q. What do you do next? When do you stop? There's no guarantee to terminate when you use axioms to try to prove something that is not a theorem. But on the other hand, if you use resolution, you have to stop. Okay, like we stop after 2 steps of resolution because there are no further things to resolve anymore. So it's a good thing because now we stop and we conclude and say, hey, Q is not a theorem. It does not follow the original CNF.
I got all that.
Okay.
You said that like 4 times.
Yep. But I'm just trying to compare the 3 approaches. Okay. Prove using the axioms of Boolean algebra, which is normally how you prove in a math class. We have resolution and contradiction, right? Those 2 go hand in hand, and then also truth table. Truth table has to terminate as well, right? Because with only 4 independent variables, you have a fairly large table because you have 2 to the power of 4, which is 16 rows, right? But 16 rows is still finite. Once you work out all 16 rows and you say, okay, I find one row where the CNF does not imply Q, then you have a conclusion and say it is not a theorem. It does not follow.
Could you just get to that point and stop?
Yes. Yep. With a truth table.
Yeah.
But the homework assignment does call for using resolution and proof by contradiction. All right. So are we good with this homework assignment? Yes? Okay. All right. So I'm going to give you guys a new homework assignment. It's not long, it's not big. It does involve some thinking, okay, but it is not really big. So let me move on to that one. It is in discrete probability over here. I got rid of some of the kind of nasty ones that I have used in previous years. So this is the one that we're going to use for this year. And there's a 1 here. It's not a typo, because I intend to give you some more later on, but this is the only one I'm going to give you for this week. So I'll just read the question and see if you guys have any questions about the assignment. The Lee family goes on family vacations 5 times per year. These 5 vacations are at specific times of the year, so they want to go during the winter break, spring break, early summer, late summer, and Thanksgiving. Oh, okay, I think I got 6 over there. But anyway, the time frames are locked, okay? So they have very specific time frames for family vacations, and 5 of those. The cost of airfare, hotel, and other vacation expenses are definitely sensitive to the time of the year. Okay, if you have ever planned for trips yourselves, then you will quickly find out that, hey, there are certain times of the year that you do not want to go other places. Like around Christmas time to New Year time, that's a really bad time because things are very, very expensive. But if you're not in school and you want to go like 2 weeks before Thanksgiving, it's dirt cheap because nobody goes during that time because everyone is trying to save up for Thanksgiving for the big trip. So nobody except for business trips, want to occur during that time. So anyway, so you have to kind of keep this into consideration is the vacation expenses are sensitive to the time of the year, and then each vacation has a very specific time frame, and there are 5 of those. For the next year, 2017 to 2018, the family as a whole picked out 20 destinations of interest. So that means they just look through all the tool books and say, well, I'm interested in this, I'm interested in this, and so on and so forth. So there are maybe 4 family members, and each person picks up 5 distinct destinations. So now we have a total of 20 destinations of interest. And the family may consider going to the same destination more than once per year. Okay, like if you want to go to Victoria and go to Butcher Garden, sometimes if you go in the spring, it looks completely different than going in the fall. So you can potentially go to the same destination twice or 3 times or even all 5 times per year. Is that okay? All right. Okay. So Tom comes up with a plan to combine cost of the trip and family ranking to totally order the destinations. In other words, I'm hoping you guys still remember what is totally ordering. Total ordering. Do you guys still remember that?
Yeah.
It means that there's a way to compare any 2 things. Okay. So Tom comes up with a way to combine the cost of a trip and family ranking, depending on how many people rank this as the highest ranking destination, to totally order the destinations, and also based on the time as well. In other words, given a particular destination and a particular time of the year, Tom can tell you how it ranks, according to the whole family and also according to the cost of the trip. Okay, and he can compare any 2 things you give him. He can compare. Okay, like we want to go to Lake Tahoe in the spring, and we want to go to Hawaii in the summer. How do those 2 compare? Which one is considered better? Okay, he can tell you that. Is that okay? All right. All right. So Tom's job is to find the best 5 vacation destinations for the entire year based on this particular total ordering. How many possibilities does he has to go through to optimize, to basically say, okay, based on expenses and based on ranking, we are going on these 5 vacations this year, and those are the destinations. So that's the question, okay? The trick about this one is you can go to the same destination more than once, and there's no limitation of how many times you can revisit a place. Is that okay? All right. So think about this one, okay? Let it soak a little bit. I made the due date next Monday, but I will probably consider moving it to next Wednesday. So this way, if you guys have any questions, we can talk about those on next Monday. Then you have one more day to turn it in. But at this point, just kind of start thinking about it, okay? And then we'll talk. We'll come back and deal with this later. Are there any questions about the assignment itself? Anything about here that is confusing, that is not clear?
If it's all ordered, wouldn't you just do the top 5 on the list? Like he's got a list of all 20.
No, he has a way to compute the numbers. So in other words, you feed in the destination, you feed in which vacation of the 5, and he comes up with a number. Okay. That's all that's basically all that is. Okay. So now Tom needs to find out, okay, what is the best way to arrange the vacations of that year. So now you have to say, okay, so how many possibilities does he have to think about in order to find the optimal? Okay. And you're not, okay, let me just also add that you're not going to sort, so you cannot just come up with all the numbers, sort, and then find out which 5 are the top ranking ones.
Yeah, that's what I was thinking. You just create the list and take the top 5.
Okay. Maybe I should ask this question in a different way. So how many ways can he arrange family trips? I think that would be a better way to ask it. So I'll change the question itself just to make sure that because there's a particular thing I want you guys to think about. So I have to kind of structure the assignment to ask that particular one. Okay, so I'm going to change the question slightly. probably change this part here. How many ways can Tom arrange the 5 family trips? There we go. Okay, so the concern is not, what is the quickest way to find the best 5 vacation destinations. It is, how many ways can Tom arrange the 5 family trips? Yep.
So I was confused at first. It seemed like you wanted to know how many items were in his list, how many total possibilities there were. Now you want only the total 5 best ones that he can choose?
Nope, not how many ways. Just that's the question here. We are not even concerned about finding the best 5 vacations. So forget about this part. I want you guys to think about using permutations and combinations. So we are not trying to solve the problem. I think I want to do a cross out.
So it's like how many unique years?
How many unique ways can he arrange these 5 families?
Like, because you could go to Tahoe 5 times,
Right, that's one way.
and you could go to Tahoe 4 times and somewhere else.
So, but then it becomes which 4 times, right? Because if you go for the first 4 trips, and then the last one is to Hawaii, that's one way to arrange
Hawaii
it.
first, and
Then it becomes another way to arrange it. I have to really filter what I say, because if I use the word that is actually in the back of my mind, that would have given away the solution. So I just have to say way. Mm-hmm. It's very Taoist.
yeah, the way.
The way, yes. Okay. But I gave you some examples already, because if you have the first trip going to Hawaii and then the other 4 trips going to Tahoe, it is considered different from the first 4 trips going to Tahoe and then the last trip going to Hawaii. Yep.
I just thought it was, he had a list of like 20 and then he picks the top 5, like in the ranking.
Nope. So we're not even concerned about how to pick the top 5. We're not just concerned about how many ways can he arrange these 5 family trips. You have 20 destinations, and then you have 5 time slots. Okay? And you can repeat. You can go to the same destination all 5 times in the year. So if they have a really nice vacation spot in Lake Tahoe, it is inexpensive, it is great, everybody rank it first, they can go there like 5 times a year. Okay? On the other hand, you can also have things all over the place, and then they would go on different places.
So every time he arranges it, there's only going to be a total of 5 options.
5 trips, yes. So there's a total of 5 trips, for that entire year. But for each trip, you have to choose, which destination. But you can repeat destinations. Okay. So you can go like 3 trips to Hawaii and then 2 trips to Alaska. But to Alaska, it depends on which time of the year. What time of the year? Because you may not want to go in the winter.
Start. Cold.
Very cold, yes. So are we good so far? So when you guys need to ask questions about this particular assignment, you might want to come up with a scenario and ask me about the scenario. Okay. All right. So I'll leave this alone for now. Okay. I'll let your slow cookers cook a little bit. As I said, the due date is currently next Monday. I'm gonna change it right now. Might as well change it to the 19th. So it is due next Wednesday, which will give you guys a chance to ask questions on next Monday. We have an exam 1 schedule on this particular Wednesday. Just a quick reminder. All right, so I'm going to save this and return to course. So what we'll do next is, we have to go back to discrete probability just one last time, because I add the section here. Remember last time when I was trying to work out the problem, my solution in class is different from the solution in the notes, and that's because I was wrong in class. Okay, so It's about this part here. This particular section is new. So let's go ahead and revisit what the problem was. Okay, the problem was I have a class, let's say 35 students. I want to figure out, okay, what are the chances that 5 students in the class have exactly the same birthday, and the other 30 students have all distinct or unique birthdays. Remember that problem? Okay. So the so the way I formulate the problem is, okay, let's go ahead and pick out 31 days out of 365 days. Okay, I have to pick out 31 exact different days in a year, because we have 30 people with unique birthdays, and then the 5 sharing one single birthday, and that's why we need 31 birthdays. Okay, so once we have that, then the question is, okay, now that we have 31 birthdays, how can we arrange the assignment of birthdays to people in the class so that we can count how many ways can we arrange that? Is that okay so far? All right. And in class, I was using combination, as how many ways to do it. In other words, for this section here, I was using combination instead of permutation, but permutation is the correct way to do it. Okay, so let's see how to look at this problem so that it makes sense to use that approach. Okay, in this particular case, I also use an example and say, okay, while you have doubt, you want to make sure that you can work out a sanity check using a much smaller case. So in this case, I want to simplify the problem and check for sanity and see whether it should be combination or permutation. And instead of making this problem complicated, this is what I'm going to do. I'm just picking 3 days out of the entire year. I pick Pi Day, April Fool's Day, and Cinco de Mayo. That's the 3 possible days. And instead of looking at things that can duplicate, I'm just saying, okay, let's say we have 3 people. We have Pat, Sammy, and Kelly. And the question now is, with 3 possible birthdays and three people, how many ways can I come up with assigning different birthdays to different people? Is that okay? So the ordering in this case is saying the first person will get Pi Day, the second person will get April Fool's Day, and then the third person is going to get Cinco de Mayo. And this is one way to assign it, which means if Pat is getting Pi Day, Sammy is getting April Fool's Day, and Kelly is getting Cinco de Mayo. Is that okay? That's one way to assign the 3 days to these different people. And then this is a different way to assign the 3 days. Pat is still getting Pi Day. Kelly is getting April Fool's Day, and then Sammy this time is getting Cinco de Mayo. Is that okay? So when you look at it this way, with a very simplified case, we end up with 6 ways to assign 3 different possible dates to these people. How come it's not 9? How come it's not 3 times 3? Because when you think about it, it seems like, okay, we have 3 going this way, we have 3 going this way, so the table should have 9 entries. How come we only have 6 entries here? Because the duplicates you cannot count. Yep, exactly. So in this case, once we use up a day, the other person cannot use that day anymore. So it's not a straight multiplication anymore. Is that okay? All right. Okay. So as a result, we have to use the permutation of choosing 3 out of 3, and not the combination of choosing 3 out of 3. So this is a quick and easy sanity check by simplifying the problem to a point where we can enumerate all possible cases and then just do a count. It's like, okay, bing, 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 bing. Oh, okay, it's not combination. Combination does not work. The other way to look at this, okay, I'm going to use the whiteboard for a while. It's not going to be anything complicated. You can just draw a small picture. So the way I look at this is I pick out 31 days out of the entire year. And then what I do is I write those days down on tiles. Okay, just imagine there are a bunch of tiles, in the classroom. So I write down the days that I have picked out on tiles. So let's just pick 4 for that. And then what I want to do is to say, okay, out of the 35 people in the class, I want to, in this case, let's say out of 4 people, I want to find out how many ways can I make 4 people stand on different spots on these tiles. Well, in that case, ordering is definitely important, right? Because whether a person stands here or a person stands here, they're considered different. And that's why it is permutation, because ordering is important. So that's the other way to look at this problem and explain why we have to use permutation and not using combination. Once we have the dates picked out, the number of ways to assign those days to people in the class, it's a question of permutation, it is not a question of combination. Is that making any sense? Okay. So I just want to re-explain this one because I got it wrong in the first place. All right. Any other questions about this one? No other questions? So this part is new, okay, so I just want to emphasize that, in order to clarify this, I wrote this section here, just to clarify when do we use, permutation, when do we use combination, and how to perform a quick and easy, sanity check. If you have a question about, okay, should I use permutation or should I use combination, do not think of those problems as a general problem, like n people with r people sharing the same birthday. Think of concrete examples using much smaller numbers, because that will really help you think about, oh, okay, so that's how it is. Then you try to fit, whether it's combination and permutation to fit that model. So it's a good way to validate. Okay, is that okay so far? Okay, if there are no questions about this, then we are also going to continue to talk about. We're moving on to the next section, which is about discrete probability distribution. But I'm hiding some other stuff in here too. Okay, so we'll first talk about Pascal's identity, and then we'll talk about the binomial theorem, because you need Pascal's identity to prove the binomial theorem. Pascal's identity is, okay, I'm not going to use Pascal's identity to begin with. We'll use Pascal's triangle, to start with this one. Okay. This is Pascal's identity, but it is really just a fancy way to look at Pascal's triangle. Okay, so forget what you see on the projector at this point. We just want to talk about Pascal's triangle first. Okay, what does it look like? What is Pascal's triangle?
You have one running down the diagonals, and at each interior point is
Okay.
equal to the sum of the two above. Or you have one running down the
Okay, we start with the tip of the triangle, which is 1, right? Then what is the next row? How do I make a triangle out of this? 1, 1. Okay, very good. And I have to do the ones like this, okay? And then what about the next row? 1, 2, 1, okay? It is the extremes of the triangle, they're all ones, okay? But when you look at the elements or the items in the inside, then you have this one being the sum of these two. So that's why we have the 2, and then we have the 1 here.
I mean, you can always just pretend there's zeros everywhere else.
Yes, you can always.
And that's why 0 plus 1 is 1.
But then you still have to explain that 1.
Yeah.
That 1 has to be there. By definition, you have edges of 1.
Yeah.
Mm-hmm. Okay, what about the next row? The edges are 1s, okay, so
3.
So you have 1 plus 2, which is 3, 2 plus 1 is also 3, and then the next row, once again, we have edges of 1, then we have a 4 here, because 1 plus 3 is a 4, 3 plus 3 is a 6, 3 plus 1 is a 4 again, and so on. Okay? Do you guys remember what is Pascal's triangle now? I mean, now that you are looking at it. Okay, what do we use Pascal's triangle for? Sorry?
Factoring.
For factoring, for binomial, something, sorry, go ahead. Expansion. X plus y to the power of something, right? Mm-hmm. X plus y to the power of 0, to the power of 1, 2, 3, 4, and each one is a coefficient of the power of one term times the power of the other term. Are we doing okay so far with why you have seen Pascal's triangle before, and this is what it looks like? Okay. Okay. So when you look at the projector, this is really just a fancy way to say the same thing. Okay. So let's check out this definition of Pascal's identity, and let's interpret what it means. The first part is a quantifier, it says it for all k, such that k is an element from 1 to n minus 1. Okay, we're talking about integers here. So we are talking about k being 1, k being 2, k being 3, all the way to k being n minus 1. The following has to be true. Okay, that's why there's a name of identity, because we're trying to say two things are exactly the same. So we are trying to say that this term here, which is n choose k, because when you look at the big parentheses with n on top and k below, one way to say that is n choose k, but we also know that as the combination of picking k items out of n items. Okay, it's n choose k is just a quick way to say it. So the sum of n choose k and n choose k minus 1 is n plus 1 choose k. Okay? Well, this is not a given known fact. Okay, this is a theorem, which means we should be able to prove it using the definition of combination, factorial, and a whole bunch of other things. Is that making any sense? All right. So we want to look at that and look at the Pascal's triangle first. Okay, this part is not in the notes, but it may be helpful to you. So we look at the well, let's look at this one here first. Okay, so with this one here, it is saying, okay, 3 choose 2 is 3. 3 choose 1 is 3 as well. The combination, when you add up the 2, it is 6. But 6 is also 4 choose 2. Okay, so it does work out in this case. In Pascal's triangle, which part am I talking about? Where's my 3 choose 2? Well, pick one to be 3 choose 2. The other one is 3 choose 1. Okay, where's my 4 choose 2? That is my 4 choose 2. Is that okay? No? Okay, so the n determines which row we are talking about, and then the k is determining the position within that row. Okay? So we have 1 choose 1 over here. How many ways can you choose one thing out of one thing? Okay, that's exactly 1, but this is actually 0. I think there's a 0.
Yeah, 'cause
0,
that's not
1,
a
2, 3.
choice, is it?
Yep, this is 0 out of 0. Sorry. So n is determining the row, but the first one is 0. And then the k is determining the position within that row. So now with the next one, we have 1 choose something, but then we have 1 choose 0 here, and then we have 1 choose 1 over here. Is that making any sense? How many ways can you choose nothing out of one thing? There's only one way, right? Not choosing anything. How many ways can you choose one thing out of one thing? Only one way, because that's the only thing. Is that okay? The next row starts with 2, so we have 2 choose 0. How many ways can you choose nothing out of two things? There's only one way, because you have an empty set. And this is 2 choose 1, and this is 2 choose 2. Is that okay? And the next row, kind of the same thing. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And then the last one, I'm just making enough entries to map to the actual numbers. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and then 4 choose 4. There we go. Okay. So now that we can see how how we use the choose or combination to figure out the actual numbers in Pascal's triangle, can you see what the theorem is trying to state? Okay, in the theorem, we lock down the row number by n, and then we use the k to control the position within the row. Is that okay? So we just choose k based on, we choose the row based on n. So in the example here, I use 3 as n, so that means we are dealing with this particular row here. Okay? And then we use 2 and 1 to select which entry within the row we want to focus on. So we are focusing on this entry and this entry here. But what is the identity? The identity is saying if you add up these two terms, it should be the same thing as the row that handles 4 items, choosing 2. Okay? So we are claiming that the sum of these two should equal this particular value. That's what the theorem is trying to state. Is that all right? Okay. Well, but isn't this approved already? I mean, isn't Pascal's triangle already approved? It is not approved. How is this not approved? It's an example. There's no guarantee that the next row will work out correctly. Okay. So how do we prove this? Well, if you scroll down a little, if we scroll down a little bit, we'll see the actual proof here. Okay. And we'll deal with this row by row. Okay. I know this is a lot. It looks like a lot, but it's not. Okay. Okay. The first row. Let's look at this row here. Okay. I'm just focusing on that one row. In fact, what I'm going to do is to use my editor as a ruler, and I'm going to empty out the content of the editor so it's not distracting. There we go. All right, so I need to move it up just a little bit. Okay, what makes this particular row happen in the proof? What did I just do?
Just use the definitions.
Yeah, it's the definition of n choose k and n choose k minus 1. Okay. So I expand n choose k to use only factorial. I expand n choose k minus 1 to express it only using factorials. Okay. So that's good. Let's move on down one row here. What about from here to here? From the first row to the second row. What did I do? It's really, really minor. That's why it's so hard to find.
Rearrange the denominator on the second.
Exactly. I rearranged only this part here. Okay, so I have n minus and then k minus 1 here. By rearranging things a little bit, I can say this is n minus k, the difference, plus 1. The 1 becomes a plus 1 because we have negation on the negation. It becomes addition. Is that okay? So, just basic algebra stuff. Okay, let's move on from the second row to the third row. There we go. Okay, what did I do this time? This time it looks a little bit more different.
Common denominator.
I think I just added a k.
Looks like you multiply top and bottom by k.
Sorry?
Did you multiply top and bottom by k on the second equation?
Well, let's see here. I added this k here. Okay, this is new, right? But I also changed this k minus 1 factorial to k factorial. I think I skipped a step here because I should have just said, k times k minus 1 factorial is k factorial. But that's basically how I move from the second row to the third row. Is that okay? In other words, I multiplied both the numerator by k and also the denominator by k. But when you have k times k minus 1 factorial, you end up with k factorial. And that's why we ended up with a k factorial here. Okay, all right. So, but this is actually a very neat trick. Then we can move on to the next row here. This is the next row. Okay, so what did I do here?
Times it by 1 over k n minus k plus 1.
I divide both the numerator and the denominator by n minus k and then the whole thing plus 1. By doing that, I changed n minus k plus 1 factorial to just n minus k factorial because I just took out that term from that factorial. But since the numerator doesn't have that term to begin with, I have to express the division, or express it as a denominator for just the numerator part. Is that okay so far? Okay. But why did I do that?
Combine like two.
So that the
Add.
denominator would be the same now, right? So because the denominator is now the same, the next step is, oops, okay. Let me scroll a little bit more and hide just that portion. There we go. Okay, so what did I do this time? I didn't do a single thing about the right-hand side. What did I do to the left-hand side? Yep, exactly. I just multiply n factorial by 1, but that 1 is expressed as n minus k plus 1 divided by n minus k plus 1. Is that okay? So now my numerator also has a common denominator. N minus k plus 1 is in both cases. So that means I can now combine it like that. Is that okay? I factor out the n minus k plus 1, divided by n minus k plus 1, and then just combine the numerators. Is that okay? Okay. And then from there, I take n minus k plus 1 and just move it to the denominator again. But now my numerator becomes n plus 1 factorial minus n factorial k plus n factorial k. Okay. Is that part making any sense? Okay. Because I combine two steps here. The first step is to take this n minus k plus 1 and just move it to the denominator so it becomes here. Is that okay? But the second step that I did is a little bit, well, it's actually not complicated. I'm just using distribution. So I distribute so that n factorial n plus 1 becomes one term, n factorial minus n factorial times negative k becomes the other term. I separate those two out. But when I look at n factorial times n plus 1, it becomes n plus 1 factorial. And then the other two terms, these two cancel out. Right? Because you have a negative n factorial k, and then you have a plus n factorial k. So these two just cancel out to 0, and the numerator is now done. The denominator can do some work, because I have n minus k factorial times n minus k plus 1 plus 1. So the whole thing can be now combined to n minus k plus 1 factorial. Is that okay? And what just happened between these two rows? I just moved things around a little bit. I grouped the plus 1 next to n, and then the minus k as the last thing that I want to do. So now the theorem is pretty much proven. Because the other way to look at this is n plus 1 choose k. Are we doing okay so far? So within this proof here, which part do you think is the trickiest? Or which parts do you think is the trickiest? If you are to prove this, okay, most of these is just normal, algebra. But there are certain tricks here that is not like quote unquote normal algebra. Yep.
Can't you also do this using the combinatorial definition? Like you can say n plus 1 choose k. That's the number of ways that you choose k people from n plus 1 people. Now you can just pick one guy, set him aside, and say, okay, hey, now we'll split it into two cases. Case 1, I'm not going to put him in my group, in which case you have n choose k. Case 2, you are going to put him in your group, in which case you have n choose k minus 1. And those are the two exclusive cases that are that completely split the set. So n plus 1 choose k is equal to n choose k plus n choose k minus 1.
It doesn't sound as rigorous to me.
It can be like made rigorous with all types of set, with like set notation and whatnot, but it's essentially the proving it the way mathematicians would do it by like focusing on the concept rather than the algebraic manipulation.
Well,
Is,
I may not be a mathematician, but I personally feel a lot more comfortable when every step can be proven by using just algebraic, expression manipulation.
Yeah, that doesn't tell you why it's true. It just gives you.
But I don't care why. I just need to know whether it is true or not. Because when you associate why it is true, then it's not how should I put it? It is not. I was about to say math anymore, but I really should not say that. But I feel a lot more comfortable when I can prove things really step by step using just normal algebra, using things that we know for sure is true. The other way, may be provable as well, but you will have to state it in a very clear way and say, okay, one way to do it is this way, one way to do it is the other way, and then show that both paths, would lead down to the same conclusion. Yep.
I was wondering if you feel that way because, like, I think it was your dissertation you were telling us about the way that you're describing would use the English language, but this way uses
Yep.
math, and so it's much harder to misinterpret the math than it is the English.
Right.
Is that where?
I think that is actually where you're interpreting my preference correctly. But that can be just a personal preference. I don't think it is, like there's only one way to prove something right. But my personal preference is to do it this way, so that I did skip a few steps in case you haven't noticed, okay? I did skip a few steps where I should have broken up into smaller steps, but I thought those were somewhat obvious, okay? So, but they're not big skips. I'm not skipping a lot of steps, okay? And by the way, this is, this proof is not copied anywhere from the internet. This is actually my own proof. I look at the theorem and go like, maybe I can prove this, and I just decided to work on this myself. So are there any questions about this one? Yep.
I say the tricky thing for me is knowing like the factorial simplifications you did.
Yes.
Yeah. And factorial times n plus 1.
You are absolutely correct.
On that n plus 1 factorial.
So the real trick to this proof here, okay, is this thing here. Okay. So the real trick to this proof is you have to recognize k. This is the trick, okay? This is the most important part here. Now, k is just a particular variable, okay? But the point is, if you have a quantity minus 1 factorial, and then you multiply that to 1 more than that quantity, then you end up with the 1 more quantity itself factorial. That trick was used multiple times in this proof. Yep.
What about when it's plus 1?
Same thing. Okay, so the other way to look at this is to say k plus 1 times k factorial is k plus 1 the whole thing factorial. It really is the same thing. But it's a way to look at the product between a number and a factorial and turn the whole thing into another factorial. And of course, the other way to do this is to do a division. In other words, you look at k plus 1 factorial, and then you say divided by k plus 1, then it is k factorial, which is really just the same thing as a different way of looking at this equality here. You just divide both sides by k plus 1. But that's the trick, okay? This is something that's new, okay? If you're not used to this type of factorial algebra, this is the tricky part.
And if you write it out, the factorial, you can see it better.
Say again?
If you write out the factorial, you can see it better.
Yes, when you expand it, you can see better. Yep. All right. So are we doing okay so far with this one? Any questions about this particular proof? Okay. I think next time when I prove something myself, I'm going to write down some notes here, like what is occurring in my mind, because I want to share with you guys, how I do the proof, but that's really hard to explain. It's kind of like, asking, Van Gogh and say, how did you come up with this? He just go like, I don't know. Or asking Einstein, how did you come up with relativity? He would just probably say, I don't know. It just occurred to me one day.
Wasn't that the thought experiment of him on the bus and what would happen if you were approaching the speed of light?
Yes, but we normally do not think of terms like that. The trick to relativity has to do with you're locking down the speed of light itself. So how do you make everything fit when the speed of light itself cannot change? Because when you throw a rock out of a car, okay, let's say you can throw normally at a certain speed, and your car is moving at a certain speed. Right. So when you throw a rock out of the moving car, then the speed of the rock is actually the sum of the two speeds. So that makes sense to us, except when it comes to the speed of light, it does not apply. Nothing can be faster than the speed of light. So making that association and say, okay, what if I want the speed of light to be constant and everything else is fluid? That is the biggest discovery. That's the one single question that is that's the question to ask in the case of relativity is what if I lock down the speed of light and make everything else fluid?
Because the parts had been there already, he just...
Right.
So you're saying if you're going the speed of light and you throw something out, it can't go faster, so you want to be the sum of the speed of light plus what you threw.
That is correct. Well, but what happens is the time is now different. So they're all going at, nothing can exceed the speed of light. It's just that when you look at the time, it is now different, and that's why that's the part that is ingenious about relativity is you change everything else to make the speed of light constant. Is that okay? Okay, this is not quantum physics or relativity, so I'm just using that as an example. Digression. All right, so that's Pascal's identity. The next one up is the binomial theorem, and we'll wait a little bit for it to be rendered. Yep, there we go. Okay, so the binomial theorem is to say when you, for all n as a natural number, so that includes 0, 1, 2, 3, all the way up to any number you can think of, any natural number. The theorem is saying, okay, 1 plus x, the whole thing to the power of n, is the summation where I goes from 0 to n, and then each term of the summation is n choose I as a coefficient times x to the power of I. Well, that's a really fancy way to say, okay, for instance, if you want to use a concrete case. So whenever you look at something like this and go like, whoa, I don't really know what it's talking about, think of a particular n that is small so that you can actually see the actual thing. Okay, so let's go ahead and look at this using a fairly small n, okay? So we'll start with something that small, to the power of 0. Okay, well, it should be well defined and handle that case because after all, I did say for all lowercase n in natural numbers, right? 0 is a natural number. So the question now is, does it work? Okay, so when you look at the summation, I has to go from 0 to n, but n is 0 in this case. So we end up with choosing 0 out of 0 things, right? Because I is 0, so is n, times x to the power of 0. Is that equality holding? Okay, 1 plus x. Ted, you did not even tell me what is x. Does it really matter? It doesn't matter because anything to the power of 0 is 1. Okay, very good. So x to the power of 0 is also 1. But what is 0 choose 0? It's exactly 1. So the equality does hold up. Okay? And then you try to think of things that you are familiar with, like a normal binomial equation. So you have 1 plus x to the power of 2. This one we should know fairly well. So you know this one is, we know what this one is. It's 1 times 2x times 1 x to the x squared, right? This is how you already know. But do these terms fit in here? Okay. In other words, can I rewrite this as 2 choose 0 times x to the power of 0 plus 2 choose 1 I have to write the choose in a horizontal format because I cannot really use the vertical formatting here. 2 choose 1 times x to the power of 1 plus 2 choose 2 times x to the power of 2. Is that really the same? Well, let's see if we can align things a little bit. So the question is really asking, are these things matching up? Is 2 choose 0 times x to the power of 0, is that 1? How many ways can I choose nothing out of 2? 1. And what is x to the power of 0? 1. 1 times 1 is 1. What about this one? 2 choose 1. How many ways can I choose one thing out of 2? Exactly 2. So we have the 2 here. X to the power of 1 is also known as just x. Now we have 2 choose 2. There's only one way to choose 2 things out of 2 because you're having everything. So that's 1. And then times x to the power of 2, x squared is x squared. So this is a quick validation to see what the expression really means, in terms of things that we already know. Yep.
I remember pre-calc they showed us, they just do the choose values and then you go x to the 0, x to the 1, x squared, and just keep going. Adding it to your term, so you get the 2 choose 0 plus 2 choose 1 plus 2 choose 2. And then for 1 you have x to the 0. It's the same thing, you just don't have to have the x's.
Oh, okay.
But
you're only looking at the coefficients.
Right.
Yeah.
Because you always have x to the 0, x to the 1, x squared.
Right.
X cubed.
But it's another way to look at the same theorem, I guess.
Yeah.
Yep. So, but this is a theorem, okay, which means it is not something that is given to you as true. This is something to be proven to be true. Okay. So, are there any questions about the theorem itself? No questions about the theorem? Okay. So, in the text here, I just, use a whole bunch of examples, to illustrate, okay, let's see whether it is true when n equals to 0. Yep, it does. So the next thing we want to do is to prove by, this is not proof by contradiction, it's proof by induction, or in induction, proof by induction. Yeah, that's the name of it. So I want to look for the word induction. Induction, there we go. So in this case, we're going to use proof by induction. Now, proof by induction is kind of interesting. I'll give you a quick preview of what is proof by induction. There are 2 steps in proof by induction. There are 2 distinct phases. One is the base case, which means, okay, let's pick a specific case of this theorem and say that it doesn't work in this case. Okay, so that's called a base case. Once you have a base case, then we have the induction step. The induction step says, okay, let's say that it works when n equals to the number k. Okay, so if you are given that it works for n equals to k, can we then prove that it also works for n equals to k plus 1, which is the next step up? Are we doing okay so far? Okay. So let me just kind of summarize proof by induction in general, just so that you have a way to refer to it. Okay. Proof by induction. Okay. So typically, proof by induction works when you want to prove something works for n equals to 0, 1, 2, 3, 4, and something like that. So we'll use that as an example here. So the proof itself is going to say for all x in 0, 1, 2, all the way up as natural numbers, the following is true. Okay, so we have a predicate here. Don't even bother with what is a predicate. Okay, this is what we want to prove. Some p, which is an expression, is always true for this x. Okay, so this is the theorem. The theorem is this. Okay, so the way we prove it is to prove the base case first. Okay, so the base case is simply to say that, okay, let's prove p of 0 is true. And that typically is a very easy thing to do because all you have to do is to substitute the 0 into this entire big huge expression here. Okay, p is expressing some kind of huge expression. So you just substitute the 0 in place of x and show that p of 0 is true, which is usually a very easy thing to do because it's just expanding an equation, figure it out, and prove that it is true. The induction step is the really tricky one. The induction step states this: assume p of k is true. In other words, it's just an assumption, okay? You're just saying that, well, I'm going to assume that p of k is true. Use that to prove p of k plus 1 is also true. If you can make this link, if you can say, if you tell me to assume p of k is true, then I can use the rest of the algebra and the rest of the derivations to prove that p of k plus 1 is also true. That is the induction step. If you have a base case and you can prove the induction step, then your proof is done. Is that okay? Does it make sense to you? Sort of, right? Okay. So let's say we want to say, okay, let's say this is done. Okay, I can prove that p of 0 is true, and I can prove the induction step is true as well. So how do I know that p of 265 is true?
Because you could just keep adding 1.
Yep. So you start with p of 0, which is proven to be true here, and then use the induction step. You can say, oh, but this is not even an assumption because p of 0 is true. But because the induction step says the next one has to be true, now we know p of 1 is also true. How is that going to help me? Well, I can use the induction step again and prove that p of 2 is true. I just have to do this 264 times to get to p of 365, but I can get there. So give me any number, I can get there because of the induction step. Yep.
I was wondering, because the way I understand inductive logic was like, okay, the sun comes up, it's been coming up, it's going to come up tomorrow. And I'm wondering, for these proofs, is there a particular, I don't know, criteria where it makes the induction a solid basis?
Well, that's exactly what it is. Okay. So in order to, okay, let me answer this question first. Yeah, go ahead.
I was just going to say, mathematical induction is different than philosophical induction. Mathematical induction is actually deductive logic, whereas philosophical induction is a different thing. They just have to use the same word term because it's used in.
And this is mathematical induction.
Yeah. So this is actually a form of deductive logic in philosophy.
Right. So in order to apply, in order to prove whether the sun is going to rise or not, if you want to prove it by induction, mathematical induction, then we have to establish two things. The first one is you prove to me that the sun has risen at least once. That's the base case. Okay? I observed the sun rose today. There is proof that the sun does rise. Okay, very good. What about the induction step? That's the tricky part. That is the part that is usually the harder one, which is basically saying, assume the sun rises today, give me the logical steps to prove that the sun will rise the next day. I don't care about the day after tomorrow. Just show me that if the sun rises today, you can prove that the sun will rise tomorrow. Just tomorrow is fine. If you can prove that, then I can say, okay, then I can prove that on any day the sun is going to rise. But if you cannot prove the induction step, then we have no confirmation that the sun will rise on any day. Is that okay? So that's why we have two important steps here. The base case is just saying, okay, we have one concrete case where the theorem is true. Okay, it's indisputable because all we do is to substitute a particular constant into the expression and it evaluates to true, which is usually pretty easy to do. Okay? The next one is the induction step is the harder one because it basically says if we give you the assumption that P of K is true, okay, how do you use this as a fact, okay, to help prove that P of K plus 1 is also true? That is the difficult part. And what does this have anything to do with programming? Especially for those of you who have taken or are taking cisp440. Induction and some kind of algorithm go really hand in hand.
The recursive.
Recursive algorithms. Very good. Okay, so why do you think these two things are related?
Same thing, you have to prove a base case.
If you want to prove the correctness of a recursive algorithm, then you can prove the base case first, okay, and say, okay, the recursion has to stop when the input parameters are like this. Is that correct? Yes, you can prove it because it's usually fairly simple, right? Then you say, assuming the recursive algorithm works for case n, and now I have one step bigger, can I say that, okay, kn plus 1 is also correct? But you have the assumption that case n is already correct. So that's why proof by induction or mathematical induction works really hand in hand with recursive algorithms, or anything that has loops too. Because loops actually is a kind of loops and recursion are pretty much equivalent. You guys know what I mean by that? It means if you give me an algorithm that has no recursion, but it uses loops, I can always convert it into a recursive algorithm that does not use loops. And the vice versa is true as well. If you give me something that is recursive, but has no loops, I can always turn it into something that has loops,
Because there's a
but no
terminal-
recursion. Huh?
Because there's a terminal condition.
No, there's just a way to convert it. It's a very mechanical way to convert anything that is recursive into something that is non-recursive, and vice versa. There are programming languages with no loops, so you have to do things by recursion. Yeah, go ahead. Sorry?
Lisp has no loops. Lisp has required recursion.
Yes.
And the way to work is using a stack.
The same thing with Prolog. Okay, so we are not going to be able to finish this entire proof today, but I do want to at least show you what needs to be done in order to prove this theorem. So I will just give you the outline, and then we'll continue this discussion next Monday. The base case is easy in this case, because the base case simply means I want to pick n to be the smallest of all the natural numbers, which is 0. So this is what I need to prove. Is this number, okay, which is on the left-hand side of the equality, is it the same thing as this number on the right-hand side? The number on the right-hand side is basically 0 choose 0 times x to the power of 0. Both of these we evaluate to 1, so we have now established the base case. Is that okay? So now that we have established the base case, then we want to say, if I can assume it works for case n minus 1, pick some n, can I show that it works for n? In other words, assume this is true already. So when you look at the highlighted portion, it really is the theorem. Okay, I'm just copying stuff from the theorem, but only applicable in the case of n minus 1. But this is assumed. In the induction step, you assume that it does work up to a certain point, n minus 1 in this case. So my question is, assuming it does work up to case n minus 1, can I establish this implication that it also works for case n? That is the biggest question. Are we doing okay so far with this? Yep.
I thought it would be n plus 1.
Well, if I use n on this side, then it will be n plus 1 on this side. They just have to be off by 1.
Okay.
Yep. So I'm not going to show you the entire proof because it is somewhat lengthy, but we start off with this thing here, which is actually this thing here, right? And then we end up with this thing here, which is this thing over here. Okay? But what is in between? Now, in between, there are some really kind of boring stuff here. Okay, let me see if I can turn on my scrolling feature. Smart scroll, where is that? Content? Do you see smart scroll somewhere? Auto scrolling, there we go. Okay, let's see if that is going to help us. Yep, there we go. Okay, so when you look at the derivation, I just want to give you one place where the assumption is utilized. Actually, if I look at here, by induction base, okay, this is where the this is where it comes in handy, because I took the x plus 1 out of x plus 1 to the power of n. I took one single term out. Then it becomes the subproblem. And then once I have the subproblem, I can now re-express that using the first part of the theorem. In other words, I expand x plus 1 to the power of n minus 1, which is this part here. I re-express that using this term here. That is how I used the assumption in the induction step. Is that okay? Okay, so don't worry about this. Okay, just focus on studying for the exam on Wednesday. We'll continue this discussion on next Monday, but it will be really helpful if you can read some of this before next Monday.